In this video, we'll talk about the general method for solving implicit differentiation problems and how you can approach solving them. So how do we work with this method? So to start, we're generally given some expression of the form f of xy equals 0. There might be stuff on both sides. There might be a number on one side. It doesn't matter. You're given some expression, some equation here in terms of both x and y. So how do we find derivatives for this type of equation? Well, step one is you differentiate the entire equation with respect to x. Things to be careful of here. Whenever you see a y show up in your problem, that's a chain rule derivative because you're assuming that y can be written as a function of x. Whenever you see a y, you need to use the chain rule. Something else to be wary of is products and quotients as they show up in this problem. Make sure the quotient rule of product is also applied appropriately whenever it's needed. A standard example here is something like if you see an x times a y in your function, that's going to need a product rule because this is the function x, which I can differentiate, times the function y, which I can differentiate. You'll have to write this out as a product rule whenever it shows up in your problem. The second step is now to solve out for dy dx in the resulting expression. And thankfully, this part is never really too complicated. And that's because of the way the chain rule works. So when the chain rule hits a derivative, it puts the dy dx term on the end, multiplied by whatever stuff comes before it. So even though you have a really complicated function, it's going to be complicated stuff times dy dx. So when I want to solve it for dy dx, I can just move all the terms with dy dx to one side of the equation, factor a dy dx that will always be as a coefficient, and then divide by everything else to solve for dy dx. This really involves just moving terms over, factoring in dy dx, and then divide. Because the dy dx always shows up on the end, this will get you to something that isolates dy dx. Here's a complex example. Find dy dx if we know that sine of x cubed y squared equals y. How do we solve this? Well, we start by differentiating the entire expression. What do I see on the left? Well, I see sine of stuff. That is a chain rule in itself. So I'm going to write this as cosine of the inside function, x cubed y squared, times the derivative of the inside function, x cubed y squared, equals derivative of y is just dy dx, so that just goes there. Now I need to keep going. How to differentiate this term here? That's a product rule. So I'm going to get the cosine of x cubed y squared sitting out front times derivative of this product. So derivative of x cubed is 3x squared, the y squared hangs around, plus x cubed, the derivative of y squared, this is another chain rule, times 2y times dy dx still equals dy dx. Now we need to isolate dy dx. So to do so, I will have to expand out this left-hand side, distribute that into the parentheses, and then move all the dy dx terms over to one side. So when I do that, I will get the following. I will see a 3x squared y squared cosine of x cubed y squared plus a 2x cubed y dy dx cosine of x cubed y squared equals dy dx. I can move this term to the other side to give me a 3x squared y squared cosine of x cubed y squared equals dy dx minus 2x cubed y dy dx cosine of x cubed y squared. I can then factor the dy dx on the right, dy dx times 1 minus 2x cubed y cosine of x cubed y squared, and then divide both sides by this whole bit that multiplies dy dx to isolate dy dx. And when I do so, I will get dy dx equals 3x squared y squared cosine of x cubed y squared divided by 1 minus 2x cubed y cosine of x cubed y squared. And again, this involves both x and y, but that's fine. If I told you a point xy on the curve, you could use it to find the slope of the tangent line, and therefore the equation of the tangent line at that point. So that's a more general approach to how implicit differentiation problem works and how you can approach them to solve them, as well as an example of what looks like for a more complicated problem, the fact that solving out for dy dx is not usually the hard part because it always shows up on the end. You can isolate it pretty easily to find dy dx and then get slopes of tangent lines for these implicitly defined curves.